Assalamualaikum warahmatullahi wabarakatuh. Welcome to fifth week of our lecture for EDS subject, electrical drivetrain system subject. So in this week 5, we are going to look into the third topic. So after the second topic, which was the electromechanical energy conversion. So in electromechanical energy conversion, we have seen how do we do from basically having, for example, a magnetic field and a current carrying conductor, how is force created, and therefore the force can be later calculated, transformed into torque, and that's how in basic principle an electrical machine works. So now starting from week 5, what we're going to do is basically we are going to look into three main families of motor topologies. The first one being the direct current machines with commutator. So we call it as commutators machine, DC machines. DC machines with commutators. The second family would be later, after 3 weeks of DC machine, we'll be looking into induction machines. So it is an AC machine. And then finally, for the last 3 weeks of the lecture, we're going to look at the last one, which is the synchronous machines. So for this week, we're going to start with DC machines. And to be specific, we're going to start the first part, which we'll discuss about the no load characteristic of DC machines. So let's begin. For introduction, a DC machine is basically the most popular type of machine prior to 1980s. So why is it popular? Because it used a very simple form of controller, and due to basically the lack of a development in power electronics, it is easier to basically supply a motor using direct current, and by just varying the amplitude of the voltage, we can basically control the speed of DC machines. So due to that lack of development in power electronics, so development of power electronics, what does it lead to? It leads to basically the development of inverters. So inverters, as we are going to look at it later in the topic of AC machines, in induction machine and synchronous machine, that part of inverter or switches that we call to create that AC controllable signals. Due to the lack of that, what happened is it is easier to basically control just the speed of machine by delivering a different amplitude of DC voltages to machine. Therefore, the choice is quickly done. We industrials usually don't even think about it. It is an automatic choice to pick a DC machine with commutator to use in different application. So as I mentioned, it's very easy to control. The speed can be directly controlled by adjusting the supply voltage. We'll see later in terms of its equivalent model. So in terms of topology, what is it made of, this DC motor or DC machine? So it's made of electrically, it's made of two separate circuits. So we're going to talk about the construction of the machine electrically. Of course, there are more interesting topics as well in terms of the manufacturing process and the mechanical component of the construction of the electrical machine. But for this subject, we're going to look only at the electrical part of the machine, because in order to control it, we need to control the electrical part of the machine. So electrically, they are made of two separate circuits. The first one is what we call as field winding. So if you look at the schematic diagram of this machine over here, the field winding is basically the winding that is situated on what we call as stator. So you have the outer part, which is static, which is usually connected to the ground. We call it as ground. This part, we have a winding that goes around the what we call as stator core. So this winding, we call it as field winding. So what does field winding do? It provides basically magnetic field. So it provide magnetic field inside the machine, in which the armature is placed. So armature is this component in the middle, or we call in terms of mechanical component, we call it as rotor. So the rotating part is the armature electrically. So the armature, or the current carrying conductor, need to be placed inside magnetic field, as we've seen in Lorentz law that indicate to us how is a force or torque created inside an electrical machine, right? So the current carrying conductor need to be placed in a magnetic field. So this magnetic field is created by this field winding. So this field winding is the first part of the circuit. This field winding is located on what we call mechanically as stator. So the term of field winding, when we talk later in any of the coming slides, when we talk about the field winding means the winding that you may find on the stator of the machine, on the outer part of the machine. Okay, so we may see later in the lab, there are samples of this machine that has been disassembled. We will be able to look at it later. This field winding are wounded around certain poles. So here there is two poles, one pole on top, one pole at the bottom. So we call it as one pair of poles or two poles. So and the winding of both poles are usually connected in series. So the purpose of it, of course, to create a magnetic field inside the machine. But there is also another possibility of creating that magnetic field rather than using a coil or a winding. So you can also replace this winding by permanent magnets, because permanent magnets also create a certain magnetic field inside the machine. So there is two possibilities. In fact, later we'll see there is two types of DC machine in terms of what we call as field excitation. We can create the field using winding or electromagnet. We can also create the field using permanent magnet. Okay. And then the second part electrically is what we call as armature winding. So what is armature? Armature is the component in the middle over here. So in real picture is the component that we can see over here. It is also mechanically called as a rotor. So the rotating part. It is mounted on a shaft, and of course the shaft later is mounted on a bearing that is attached to the stator. So the armature is basically the electrical circuit, the winding that's wounded around what we call as teeth. So teeth of the machine. So we have this winding on the rotor that we call as armature. So what is the purpose of this armature winding? The armature winding is basically, it serves as the current carrying conductor, as in the simplistic Lorentz law that we have seen earlier. So this armature will be placed inside the magnetic field created by the field winding. And the current, the interesting question is, how do we deliver current to a rotating part? Because we know that this rotor in the middle over here will be rotating, right? So in order to deliver current to this conductor, this wire, this winding in the armature, what we do is that we use what we call a sliding contact of two components we call as brush and commutator. So you can see here in copper color is the conductor, and they are basically connected to this copper color surface as well. So this section is what we call as commutator. So commutator is basically the component that receive currents and then deliver it to the winding. And how does this section receive current? It receives current by a sliding contact with what we call as brush. So in this GIF animation below, we can see that you have a commutator in the middle, and in contact with the commutator is basically a brush. And this brush in fact is connected to a power supply, where current will go through the brush and being in contact with the commutator through sliding. Of course, it's a friction contact, and then it is therefore the current can be delivered to the winding inside the armature, or we call it also as rotor coils. Okay, so we need brush and commutator to deliver currents into our rotor coils or armature winding. So here in this figure over here, we can also see the brushes illustrated over here, and the sections in the middle is basically what we call as commutator. So commutator have a sections. You can see that we have different sections. The sections are connected to all the different windings inside the armature. So the rotor coils. Okay. So in general, a DC motor has a range of power which is quite large. It is not as large as AC machine, of course, but it is the range is nonetheless large, especially if you go back into the previous years, around 80s or before 80s. We use DC machines for large machines. So the power range can be varying from very small a few watts to a few megawatts. So in terms of voltage, because it is a voltage control machine, we are delivering voltage to the armature. So when we talk about the voltage, usually is the voltage of armature, not voltage of the field winding, because voltage of the field winding is usually fixed just to produce the magnetic field inside it. So the armature voltage can be ranging from a very small 6 volt to 700 volts. So it's a very high voltage. So why do we have this range? You might wonder. So we don't do any machines with voltage usually smaller than 6 volts. You may find some basically for toys machine, for example, you may find a smaller voltage, but usually in industry we don't do DC machine with less than 6 volts of armature voltage. Why? Because basically what happened so we don't have anything that is smaller than 6 volt, because why? Basically, when we deliver current from the commutator to from the brush to the commutator, it is by friction. Therefore, the contact is not perfect. If the contact is not perfect, then therefore there is a certain resistance in between the brush and the commutator, right? So the surface is not perfect. There is a certain gap and certain surface roughness that create a certain small resistances. And as you know, if you have resistances, therefore there is a certain potential difference of voltage created in between. You need to overcome that voltage in order to deliver the current onto the commutator. So that is what we call as voltage drop. So if the voltage drop can be in the order of a few volt. So if you have a smaller voltage, then the voltage drop can be a large percentage of that voltage supplied. So it doesn't make any sense to have a large portion of that voltage supplied lost inside the voltage drop of contact. So we don't create basically it will become less efficient. So we don't have a machine that is smaller than 6 volts. As in for the larger voltage, larger than 700 volt, why do we don't have them? It is because due to the, if you look at the commutator over here, the commutator have separation. They are in sections in order to deliver currents to different conductors, different windings. So in between this section, the space are quite small, and if you have a very high voltage with a very small space, what happens is you may have arcs coming out of it, where you can have currents passing from one section of commutator to the other section of commutator. So it will become very hard to increase the voltage, as the surface here will become short circuited if the voltage is too much. Okay, so that's why we have this kind of range of power in terms of voltage. I mean, not power, in range of voltage for armature winding. So this is the kind of voltage that you may find in selecting a DC machine. So here is a GIF animation of the operation of the machine. So we can see here it is an example where you have the field, magnetic field created by, not in this case by a winding, but in this case by a permanent magnet, and we can see the commutator rotating and the delivering current that's coming from the brush into the armature winding or rotor coils. So rotor coils and armature winding are the same thing. So next, what we can look at is basically for a given power. So a machine, when you select a machine, it is selected in terms of how much power do you want to deliver. So because when you want to deliver, of course, when we talk about rotational machine, rotating machine, electrical machine, they deliver their power in terms of rotational speed and torque, right? So that speed and torque in initial, they come from electrical energy. They were converted from electrical energy. If they are converted from electrical energy, it means it's the pair of voltage multiplied by current. So for a given power, when you select a machine, an electrical machine, it can be selected in terms of the voltage supplied to armature winding. So for example, you can select easily a motor of 12 volts, 4 amps. So 12 volt correspond to the nominal voltage that you supply 4 amps may correspond to the maximum load or maximum ampere, maximum current that can be drawn from by the motor. The same machine can also be offered in different voltage range, for example 24 volt, but in order to get the same power, of course, if you want it to be in 24 volts, it's going to be a 24 volts 2 amps version. So how do we do it? We do it by basically by the winding of the coils in armature would be a bit different, where you will have a 2 times smaller winding in terms of cross section. So if you're using a conductor with a certain diameter, now you need to reduce the diameter of that conductor, right? Because you are only carrying 2 amps, because the diameter of the conductor is need to be proportional to the current. If you're carrying less current, then you can reduce the number of conductor. But of course, in order to get the same MMF and multiplied by I, to have the same current, you need to coil the winding with a 2 times number of turns. Okay, so why do we have this this variation? This variation, we have it because basically it is to be flexible, to adapt with the availability of the power supply that the client has. So for example, if your client has a power supply that can only supply a current up to 2 amps, so because supplying a high current is quite expensive. So if you only have a power supply that can deliver up to 2 amps, what you need to do is you need to select a motor that is in this configuration, 24 volts 2 amp instead of 12 volt 4 amps. Okay, so it is basically for the flexibility in terms of availability of power supply from the side of the client that use the motor. So here the figure that we have over here is very interesting. So here we have basically we can see the winding of the stator or the field winding. So here in this case we can clearly see there is basically 4 poles. So 1 poles over here, so there is a section of poles over here, another poles over here, and there should be 2 other poles on top. You have 4 connectors for winding. So there is here 4 poles of a field winding. Just now we have a permanent magnet, now we have a winding. Okay, so how do we classify DC machines? So in terms of classification of DC machines, we classify them in terms of how do we create that field winding. Okay, so that how do we create that magnetic field in the stator? So that magnetic field in the stator can be created by 2 methods. It's either by having a field winding, as in over here, or by having, like in the previous slide, have a permanent magnet. So when you try to look for a DC machine, DC motor, and the first thing that you should know is that what kind of DC motor do you need? Do you need something that has a winding on the stator, or that has a field winding? Why would we want a field winding? Because we want to regulate that, that give a certain flexibility to regulate the magnetic flux or the magnetic field in which the armature are placed. If you don't need that kind of flexibility, you can use permanent magnet DC motor, where now you don't have the possibility to adjust or to modify the magnetic field inside the machine. In terms of if you choose a field winding machine, so a DC machine with field winding, where the stator you have winding instead of permanent magnet, there are certain classification of it as well. So the classification of this, what we call as wounded stator. Wounded stator means the stator have a winding, right? So in terms of this wounded stator, it can be classified further in function of the connection between the stator winding and the rotor winding. So for example, here we have in this figure over here an illustration of a stator winding. So stator winding connected to the stator core, and then we have a rotor winding. The rotor winding and the stator winding can either be connected together and supplied together. That's what we call either shunt excitation or series excitation. Series excitation means you have your stator winding or field winding and the armature winding connected in series. Shunt excitation, we'll see later what it is. It's basically more or less like a parallel connection. A separate excitation means you have completely separated. You need 2 power supply. one supply for the rotor, for the armature winding, and another supply for the field winding or stator winding. Okay, so there is this different configuration of machine, and of course they have their own advantages and inconvenience. For example, permanent magnet means you don't need to supply any energy to the field, because the field energy is not going to be transformed into mechanical energy. It's only there to basically to make it possible for the armature to create that torque or to create that force. So if you use permanent magnet DC motor, it means you'll be using less energy, so it's more efficient, but of course you don't have the possibility to adjust the magnetic field inside the machine. If you use this method of wounded, then you have the flexibility of increasing or decreasing the magnetic flux. Okay, so now let's take a look at the most important part. So now let's take a look at the most important part of using an electrical machine, which is producing the torque, therefore making it available possible for the machine to accelerate. So in a machine, the first thing, one of the things that is important to know is that when we look at the stator winding or the field windings just now, we can see that there is a certain number of poles. So in DC machine, we can find usually either 2 or 4 poles, and this number of poles is basically does not have any importance or any relation to the speed of the machine. Speed of the machine is not related to the number of poles. The number of poles can be related to basically the choice is based on the economic reason or manufacturing process reason, right? But on armature, what important is to look at the commutator. To look at the armature, and in the armature we have seen just now the most one of the most important component in the armature. Of course, the important component is the winding or the coil in which the current will circulate and react to the magnetic field, producing the force and the torque. But it is very important to look at the commutator, because it's the commutator that ensures that the current is delivered, and it need to ensure that the current is delivered in a constant form, in a certain pattern, that stays consistent regardless the position of the rotor. Why do we need so? We need so because if you remember in the part where we study the electromechanical energy conversion on Lorentz law, in order for a rotor to rotate, we need basically a certain direction of a current. Okay, because we know the magnetic field now, we are going to consider that magnetic field created by the field winding is going to be constant. For example, we'll take this case over here. So this is a 2-pole machine, this is a 4-pole machine. The principle is the same. Let's have a look at the 2-pole machine. If we have the 2-pole machine where we have a north side of the magnet on top and the south side of the magnet at the bottom, we will have the magnetic field usually pointing from south to north. So the magnetic field is pointing upside. So and then the second fingers is the finger that is directing following direction of current, and we will have the third fingers, the force created due to those interaction. Okay, so we see that if the magnetic field is constant, then the force that is created will be depending on the direction of current, whether it's pointing this way or we pointing outside of the screen or the paper. So the direction of torque, when we are operating the machine, we need the torque to be always in the same direction, right? So imagine if you are using your motor, DC motor, to be used in your electric scooter. So if you are accelerating your electric scooter, of course you want your torque to always be in the same direction, so that the acceleration is smooth in one direction. So in order to maintain that torque in consistent direction, you need the current to be always in the same direction. So the current in a certain in a certain location of the armature need to be always in the same direction. So let's have a look here. For example, the current, in order for this machine to rotate, the current on top over here need to be in the direction of basically coming out of the screen, and the current at the bottom on the south side need to go in the opposite direction, going into the screen. So this, as the armature or as the rotor rotates, if the current stays in that direction, what happen at 100-degree later, you're gonna find that the current that goes out of the screen will find itself at the bottom. So now at the bottom, the direction of current has changed after 180 degrees of direction. Therefore, the direction of torque will also change. Let's imagine at 0 degree now, the torque is rotating clockwise. But if the armature have completed 100 degree of rotation, now the current has induced a torque that goes counterclockwise. So that is not what we want. Therefore, what we need is basically to have the same pattern of current direction inside the machine. So that is the purpose of armature sections just now and the brush. So that there is what we call commutation, that the same current, so the same current direction is always sent to the same location regardless the position of rotor. So here in this figure over here, of course, this rotor will be rotating. So for example, this conductor A over here will at 180 degree later move to position B, but if there is commutator, the contact between brush and commutator, the conductor A, which will become at B later, will always receive the current in the direction of B instead direction of A. Okay, so that's the importance of commutator. So the first thing, in order to produce the torque, consistent torque, we need commutator and brush, and we need that the pattern of the current is always in the same pattern regardless the position or the rotation of the rotor. So that's the first thing. And then the second thing that that is important to know is related to basically the relation between current and torque. So what we observe is basically if you operate an a DC machine, as you increase the torque or you increase the resistant torque towards the machine, you're going to observe that the machine draw more and more current from the power supply. So imagine you have a DC machine that is rotating at no load, means it's not attached to anything, and you try to break the machine. I mean breaking as in not break it into two, but put a friction into it so that it slow down. What's going to happen is that if you monitor the current will increase, which means that the motor is drawing the current in order to overcome that frictional frictional torque. So the relation is basically there is a certain relation to that. The relation is the torque produced by the current carrying conductor I inside the magnetic field B is the torque equals to a certain coefficient KT multiplied by flux. So this is the field flux that's created by the stator stator field. I mean by the field windings multiplied by the current inside the armature. So KT is what we call as torque constant. So it's constant. It is depending on the size of the machines and other topological or geometrical criteria of the machine. Phi is the flux from the field excitation. So the field excitations mean if it is a permanent magnet, then the flux from the permanent magnet. If it is a wounded stator, then it is the flux from the winding. And I is the current inside the armature of the rotor. Okay, so the torque is proportional to the current with a certain coefficient KT. So if we imagine that the flux is constant, let's say imagine now we are fixing the flux, so the magnetic field is either supplied by permanent magnet or by a fixed current on the winding of the stator on a field winding. So what we can see is that the torque is proportional to the current, or the current is proportional to the torque. More torque you want to overcome, then the motor will draw more current, and the proportionality is basically proportional to a certain coefficient KT. So inversing the current, so another conclusion that you can say also is that if you inverse the current I, it means you will also inverse the torque T. So it is very simple in using this DC machine. If you want it to rotate in one direction or another direction, what you need to do is just to inverse the polarity. It means if you have a brush that is connected to your winding here, so brush connected to A and B, so now the A is positive, B is negative. what you need to do is you just invert that polarity. Now your machine will have the negative torque and it will rotate in the other direction. Okay. After looking at the torque, the next characteristic in DC motor that is important to understand and to look at is what we call as back EMF, or back electromotive force. So as its name mentioned, EMF basically is a voltage. It is just like what we have seen in Faraday's law. So a voltage is created when you have a current carrying conductor that moves inside a magnetic field, right? So a DC machine is also basically the same thing. You have the conductor carrying a certain current and is rotating inside a magnetic field produced by the field winding. So there should be a certain induced voltage, or what we call as EMF, electromotive force, right? So as the armature rotates, the conductor cut the magnetic field. Therefore, according to Faraday's law, this will produce a certain EMF inside the armature winding. Okay, so this can be observed basically and measured across the brush. So if you took a certain voltmeter, your multimeter, and measure it across the brush, when you rotate your rotor without supplying any voltage to the armature, rotating the rotor alone will produce a certain voltage. So it's now becoming the machine now is operating in generator mode, and this voltage is basically what we call as EMF, right? So the back EMF, the term back EMF, because basically the voltage is countering the direction of the voltage that you supply. So if you're supplying a certain voltage, the rotor rotates, the reaction of induction will create a reverse voltage. So that's why we call back EMF. The back EMF is in a form of direct current as well. So if you have a load, then you will be able to observe a certain current. So it's also in the form of a DC, and it is generated, as I mentioned just now, across the brush. So this back EMF, noted as E, is in relation with a certain other parameters of characteristic of the machine. So basically what we observe, if you do an experiment where we put a motor without supplying any voltage to it, and we measure using a voltmeter across the brush, and we rotate the rotor with a certain rotation end, we could observe that the generated back EMF E will be equals to a certain coefficient Ke multiplied by the flux, the field flux that's created by the field winding, multiplied by n, which is the rotational speed of the rotor. So as I mentioned just now, let's imagine if we have the field flux as constant, therefore this phi and Ke becomes a certain coefficient. So what we observe is the back EMF is proportional to the rotational speed. So what is Ke? Ke is, as I mentioned just now, is what we call as a speed constant. Phi is a flux field, and n is a rotational speed. So the back EMF is proportional to the speed, and what we do is basically, if you reverse the direction of the rotation, then you will also reverse the sign of the voltage that you are measuring. The voltage also will be inverted. So using these two criteria, characteristic of back EMF and torque that we have seen in previous slide, we can basically construct a certain model of the DC motor. So the model that I mentioned just now is what we call as an equivalent circuit. So equivalent circuit is basically an electrical circuit that will explain the relation between different parameters that we have in a machine, the interaction between them. So we have from the two characteristics of the DC machine just now, which is the relation between torque and current, and the relationship between back EMF and the speed. So we can write them as, so imagine if we have a constant, as I mentioned just now, field flux. So we are gonna have a certain constant Kt of torque constant, Ke as the speed constant, or also known sometimes as the EMF, back EMF constant. So we have these two equations that's very important for DC machine. Torque equals to KT multiplied by the current. E or back EMF equals to KE multiplied by omega, which is the rotational speed. And in a data sheet of DC motor, if you buy a DC motor, basically you would be able to find these two coefficients of KT and KE. So it is the constant that characterize any DC machine. Okay, so in SI unit, in utilization of this equation, in SI unit, of course, you use all the usual SI units stored in Newton meters, I in amps. Therefore, KT is in Newton meter per amp. So it's how much torque can you produce per unit of current. E in volts, omega in radian per second. So KE, the unit, is basically volt per radian per second. So basically how much back EMF can you produce per unit of rotational speed. So that's the unit for this equation. So from this we can create an equivalent circuit. So an equivalent circuit of a DC motor looks like this. So what do we have here? What we have here is basically V over here is the voltage that we supply to our armature. So now we are considering that the field flux, or the, as I mentioned just now, as I mentioned in 3 previous slides, in electrically DC machine has 2 separate circuits. We can divide it into 2 separate circuits. The field winding, which creates the magnetic field in which the armature will be placed in, and then the armature winding. So the model of an equivalent circuit is usually concentrate only on the armature part. Why? Because it is the armature part that produce the energy conversion, and it is not the field winding that produce the energy conversion. So the field winding is basically a medium in which it is possible to do the energy conversion. It is necessary to have that field flux, but the energy conversion happens in the armature. So if you look at the armature, V over here is the voltage supplied to your armature, to your rotor, and R and L is the resistance of your armature winding, of your rotor coil, or in other names. L is the inductance. So an armature basically is a winding around the rotor tooth. So when you wind up make a winding out of a conductor, then you create basically an inductance. So it has a certain value of inductance L, right? So L is the inductance of your armature winding, and E over here, so this is basically your rotor. This two black rectangle over here, black square, represents basically your brush. So the E voltage across in between the brush is basically the back EMF. Okay, this is the back EMF. So if we look into this equivalent circuit, we can basically write an equation that relates all the parameters using using your Kirchhoff voltage law, right? So you will end up with having this equation. Okay, so if we're going to show step by step. So you have the voltage V in this direction, you have the current circulating inside the circuit in this direction, therefore you have the voltage across the resistance over here. So this is the voltage across the resistance, which is equals to I multiplied by R, right? And then L over the inductance, we have the voltage of inductor VL, which is, we know that across an inductor the voltage equals to L, the value of inductance, multiplied by di over dt. So di over dt is the variation of current across time. And then we have over here the voltage E. So if you write KVL in a loop, let's say we take this direction of loop, you will have V minus VR minus VL minus E equals to 0. Therefore, you can also write V equals to VR plus VL plus E plus E. And VR, what is VR? VR is basically I multiplied by R. VL is basically L di over dt, and E is just E. So we have this equation. This is exactly the same equation that we have at the bottom here. So we have a V equals to E plus IR plus L di over dt. So in operation as motor E, if we are operating as motor E, as I mentioned in previous slide, is going to be opposing the direction of the voltage supply. That's why it's called back EMF. So you'll get this equation. This equation coupled with this relation between torque and current and back EMF and rotational speed are basically the three equations that characterize any DC machine. So this is three equation that you have to remember. Or of course, the third equation is not to be remembered. The thing that to be remembered is basically the equivalent circuit. Then you'll be able to find back the equation. But this relation of torque and back EMF, it is something that you need to by now understand, and we will use it in the future. So after looking at all the characteristic of torque, relation between torque current, relationship between back EMF and the back EMF and back EMF and the rotational speed, and therefore deducing the equivalent circuit, the thing that is interesting to look at now is to understand or to observe the characteristic of those those equation of those equivalent circuit in different operational mode of the DC machine. So the first operation mode that we are going to look at is basically when the machine is operating in a steady state. So now we are going to look at the steady state characteristic of the DC machine. So what is steady state? Steady state characteristic is basically the state when you have the machine rotating at a constant speed and it has a constant load. So it is not a transient state in contrast to a transient state. Steady state is basically a state where everything is constant, it's rotating at the same speed, the load is constant at a certain load, and it is like you have your machine operating during, for example, during cruising. Cruising means having a constant speed, or pulling a load continuously. You might have a load, but the load is a constant and you're pulling it continuously with a constant speed. So all parameters can be considered as constant. So this steady state characteristic is very important in system design, because when we try to choose a machine, it is always we always choose it in two state. The machine need to comply or need to be able to supply sufficient power, torque, and speed during steady state and a transient state. And the most important thing is usually steady state, because steady state is the state in which your machine will operate for a very, very long time. So imagine if you have an application of paper mill. Paper mill means you have to wind up or to roll up a certain paper. So there is two phase. There is the phase where you accelerate at the beginning to get into a certain speed, and then once you reach that speed, you are basically retaining that speed, maintaining that speed for the whole operational cycle. So it is the cycle, or it is the state in which the machine will operate consistently. Okay, so it is very important to understand the steady state characteristic. So in steady state, what happened? As you mentioned, in steady state, everything is constant, load is constant. If we have load is constant, we have seen just now that is if we have more load or less load, it will be reflected in the so load is basically the resistive torque, right? So if we have more or less resistive torque or resistive load, what we'll be observing is basically we will observe it in terms of current, because there is the relation of torque equals to KT multiplied by current. So if we have a constant torque, then the current will be constant. And if you look at our equation that we have just now, V equals to E multiplied by IR multiplied by L di over dt. If we have a constant current, therefore there will be no di over dt. Di over dt will become 0, because di over dt is basically the variation of current. We have no variation of current, therefore these terms of L di over dt will become 0. There will be no influence of inductance on the characteristic of the armature circuit anymore. So your equivalent circuit in steady state will become V equals to E plus IR. The inductance is negligible in not negligible. It basically it doesn't have any influence. I'm sorry to say negligible. It won't have any influence and is neglected in steady state. So if you are noticing that your machine is operating in steady state, this part is to be removed. Now let's look in detail more in the operating different operating mode in steady state itself. So in steady state, as I mentioned, everything is constant, but there are a few categorization that we can make. The machine can be in steady state where you could have a load. So imagine that it is pulling a certain load but rotating at a constant load and a constant speed, but it can also rotate at steady state with no load. So this first part is we're going to look at no load speed. It means it's rotating at a certain speed, constant speed, but it doesn't have any load. So you imagine you have your machine, your motor not connected to any application, so it has its shaft freely. It's gonna rotate freely. That's what we call a no load operation. And when it attains a steady state, that is basically no load speed in steady state operation. So no load speed means when the motor is running with nothing to be trained or carried, the torque needed, therefore the torque needed to rotate the machine is close to zero, because torque is only developed when there is a resistive or a load at the end of the shaft that's connected to the shaft. If you have nothing that is connected to the shaft, therefore the motor can rotate freely. If it rotates freely, means there is close to zero torque, no torque at all. It's very easy to rotate. The torque is considered close to zero. So the only why do we say close to zero? Because we know the resistive torque cannot be completely zero, because in order to rotate your rotor has a certain inertia, and it is in contact with your bearing. And we also know that in order to operate a DC machine, basically there is the sliding contact between a brush and your commutator, right? So there is a brush and commutator that is in contact. Let me pause and take a sample of a rotor that we have in our lab right now. So here is an example of basically a sample of an armature of a DC machine that we have in our lab. So you can see if it is rotating freely with no load, it means your shaft at the end is not connected to any application. Therefore, it can easily rotate, no resistive torque. But as I mentioned, it cannot be completely zero. Why? Because we can see that the shaft will be mounted on, so there are two bearings on each side, here and here. So it's mounted on bearing, therefore bearing has small amount of friction, so there is a certain small resistive torque, and added to that there is basically here your commutator. So what you can see here, a black trail, so there is a black trail on the commutator. Black trail here is basically the surface on which the brush is in contact. So the brush is touching and sliding on the commutator as it rotates, right? So the sliding contact between the brush and commutator also have a certain, of course, the resistance is very small. It is very small because the surface roughness of this contact are made so that the resistance is minimal, but nonetheless it is still there. So what's going to happen is that there will be a certain small resistive torque, therefore load, but it is very close to zero, or is very negligible compared to if a machine is basically driving or trailing a train, carrying a certain real application load. Okay, so and eventually there's also the aerodynamic forces, small aerodynamic forces, because it is rotating and it is in contact with air. There are certain aerodynamic forces. So this all combined is what we call as frictional load. But nonetheless, it is very close to zero. You will only notice if you do a measurement of current in armature. if a motor is rotating without connected to any load, you will basically observe a very small amount of current compared to the nominal current that's indicated in the datasheet of the machine. So if we consider, for example, in this case here, we're going to consider if we consider that frictional torque is negligible, therefore torque in the relation between torque and current, torque is negligible, torque equals to 0. Therefore, in this relationship, automatically you're going to see that the current should also be equals to 0. So what happens if it's 0? If it is 0, then our equation in our equivalent circuit, which was just now only reduced to V equals to E plus IR because the inductors have no effect in steady state. Now, if you are in steady state and no load, the IR part also can be eliminated. Why? Because the current is considered to be 0. Therefore, the product of IR also 0. So the voltage would be equals to the back EMF. So the voltage that you need to supply in order to rotate your machine, if there is no load, and to rotate your machine at a constant speed, the voltage will be equals to the back EMF. And we know that back EMF in the equation previously, the relation between back EMF and rotational speed, we have E equals to KE, the speed constant or back EMF constant, multiplied by phi n. So phi the field flux and n the rotational speed. So the voltage supplied is very close to the back EMF, and therefore the voltage supplied should be proportional to the speed. So if you want in the DC machine, if you're rotating the machine with no load, if you want the machine to go faster, then you have to supply higher voltage, because the voltage is proportional to the rotational speed. So in observation, what we can see is no load speed is proportional to the voltage supplied, as I mentioned just now. No load speed is inversely proportional to the field flux. If you look at this equation, the rotational speed here, if you bring all KE over phi over here, it means that rotational speed is inversely proportional to the flux. What does it mean? It means that if we have a constant field and we are supplying voltage, therefore the machine can rotate at a certain speed n. If we want to increase the speed n, we have two choices. It's either to increase the voltage supplied V, or if we have basically flexibility, if we have a certain control over flux, field flux phi, then we could reduce the field flux phi in order to increase n. So imagine if you have a maximum voltage supply, your power supply could only supply a voltage to armature up to, let's say, 24 volts, but you still want to go to a higher speed. What you can do is you can reduce the field flux phi so that the speed can increase, the speed n can increase. But of course, there's a remark, this could only be done if your field flux is controllable. So what does it mean is that if you have a motor where the field flux is created by permanent magnet, then it is not possible. You cannot increase the speed by reducing the field flux. But if your field flux is controlled by a field winding, then you may be able, in certain configuration, for example, a separately excited machine, DC motor, then you could reduce the field flux by reducing the current given to the field flux. So here, the circuit of the field flux is not drawn over here, right? There is no field flux circuit for this part. This is only the armature part. But if you can reduce the field flux, then we can increase the speed n. So that is what we call basically the flux weakening method. So in control of electrical machine, this is also true for AC machines later. We have a mode of operating that we call as flux weakening. Flux weakening means if with that supply voltage you attain your maximum speed, but you still want to increase your speed, what you need to do is basically you have to reduce the field flux. Basically, field flux, when you reduce it, it's in analogy, it's like you reducing the control, you loosening the control over the rotor, so the rotor can go faster. It's like a clutch basically. When you pushing your clutch, basically you're releasing the friction, and then you can rotate more. It's analogous to that. So that's what we call flux weakening method. But nonetheless, the thing that we need to understand here is that at no load in steady state, the voltage is very close. The voltage supply will be equals to the back EMF E, and of course in the case where the torque is very small, because it's not completely zero, right? So if it is very small, then the voltage will be slightly larger compared to the back EMF E. The back EMF E will be very close to the voltage supply if 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 the motor is rotating with no load. To check our understanding on the steady state characteristic of the machine, especially at no load that we have seen just now, let's try to do this exercise. So in this exercise, what we are considering basically quite a huge DC machine, DC motor. It is a permanent magnet DC motor by the manufacturer Baldor. So it's a 500 volt normal operating voltage. When we say normal operating voltage, it means that it is a voltage that can operate in steady state at all time. It can produce up to 9.1 kilowatt, has a maximum load current of 20 amps. Okay, and it has an armature resistance. So armature resistance is the resistance that you see in the armature equivalent circuit. R equals to 1 ohm. So it's a very small resistance. It is not that small. We want to have the resistance as small as possible usually. So, but now in this case, the resistance equal to 1 ohm. And there is a certain observation that is noted over here. When the machine is supplied with 500 volt, which is the normal operating voltage, and unloaded, which means that the shaft is not connected to any application, it is not a trailing or driving any application, it is unloaded, the motor run at 1040 rpm. So the motor can run at about 1040 rpm with 500 volt and drawing a current of 0.8 amps. So it draws a current of 0.8 amps. So unloaded means, as we've seen previously, unloaded means the frictional torque is very minimal. So we can see that the frictional torque is translated into a certain current drawn. Is a very small current of 0.8 amps compared to the maximum variable current of 20 amps. So the question asks us, following this observation, can we estimate the no load speed, also the no load speed, if the armature is supplied now instead of 500 volt, if it is supplied now with 250 volt, and this estimation need to be done in two cases. Either first case is when the torque is negligible, when we consider that the torque is the resistive torque is 0, which is not really the case because we can see that there is a small amount of current, but nonetheless it wants us to calculate estimate the no load speed if the frictional torque is negligible. And secondly, in the second case where frictional torque is taken into account, is considered, right? So let's try to do this. In order to do this, let's first lay down all the equations that we know related to DC machines. So the first two equation is the relation between torque and current. So T equals to KT multiplied by I. Relation between back EMF and speed, E equals to KE multiplied by omega. And then finally, the equivalent circuit, relation between voltage, resistance, and inductance. So V, voltage supplied to the armature, equals to E plus Ri plus L di over dt. And we know that in steady state, so because we are talking about steady state here over here, we will not have L di over dt. So we will only have this part of equation. So let's have a look at case 1 where we consider the frictional torque is negligible. So I'm going to write right here, case 1, frictional torque be negligible 0. If frictional torque considered to be negligible 0, therefore the current should also be equals or tend towards 0. Okay, we have a certain voltage. If current is 0, if current is 0, then our equivalent circuit just now, V equals to E plus Ri, will becomes only, so I is 0 because there is no torque, no load. Because looking at this equation, if we have 0 torque, then we have 0 load. So we have V equals to E. So the voltage supplied should be equals to the back EMF, and it is basically equals to 500 volts. And from the second relation of E equals to K omega, we know that this 500 should be equals to KE multiplied by omega. And the omega, the rotational speed here is 1000, so 1040 RPM, right? So from here we can basically find KE, the first constant, the speed constant or back EMF constant. Therefore, KE is basically equals to 500 divided by 1040, right? KE equals to 500 by 1040. And if knowing KE, looking at this equation number 2 over here, equation 2, I'm going to number the equation first, so it is easier to refer later. So looking at this equation number 2, if we have KE, and if we know one of E or omega, for example here is what is given is V, at any voltage we may estimate the speed that the machine will produce. Okay, so here it says estimate for voltage equals to 250. So therefore, if V equals to 250, therefore omega should be equals to, so from the equation number 2, omega should be E over KE, E over KE, and we know that E should be equals to V because current is 0. So here we have E equals 250 divided by KE. What is KE? KE, it was found over here, is 500 divided by 1040. So it's 500 divided by 1040. And if you do the calculation, you should find it is equals to 520 revolution or rotation per minute. Okay, so at 250 volts, it should be rotating at 520 RPM. So there's a remark here, there's an observation that we can make over here. If you look at the speed, it is basically a half of the speed that we have previously. 1040 divided by 2, we got 520. So why do we have the speed half of the previous speed? It is basically because we have the voltage now is the half of the previous voltage. So if we consider, so the relation between speed and voltage, if the current is considered 0, there is no frictional torque. In the case of frictional torque is negligible, therefore current equals to 0. Basically, the relation between speed and voltage is proportional. More speed, more voltage you supply, the more speed you have. So just now at 500 volt, you get 1040. If you reduce by 2 at 250 volt, then you get 1040 divided by 2. Therefore, that's why we got 520 RPM. So that is the first case, right? Let's go to the second case, case 2, where we consider the current to be non-zero. So case 2, we have the current equals to 0.8 amps, right? And therefore the torque, resistive torque, is not negligible. So what should we do in this particular case? So first thing that we need to do is we need to go back to the model or equivalent circuit of the electrical machine, because the case are now is not the same. It's not the same. So we had V equals to previously we considered that V the voltage supply equals to the back EMF because there is no current, but now it's not the case. We have to add the current I due to the resistive torque IR, right? So what we need to do now is to recalculate our E. Now E is not something that is known. It is something that will not be equals to voltage, but is going to be a bit smaller compared to the voltage supply, because there is some portion of the voltage supply is going to be consumed by the resistance of the winding R, because there is a certain current. So the current was mentioned to be equals to 0.8 amps. So let's do the calculation. So E, the new E, the new back EMF in the condition where the torque resistive or fractional torque is considered, E should be equals to V minus IR. So V, the voltage that is supplied previously, it was 500 minus current, so current is 0.8, right? Multiply by R, so R equals to 1 ohm. So E is equals to 500 minus 0.8, so we got 499.2 volts. So E is 499.2 volts. It is basically very close to very close to the supplied voltage. Nonetheless, there is a small portion of 0.8 volts lost into the winding resistance. Okay, so now this is our new E. So having our new E, you can therefore now calculate using the equation number 2. We can now calculate the KE. So we know that E equals to KE multiplied by omega. Therefore, the new KE is the real KE considering the frictional torque. KE, the new KE is E. So E divided by omega. So now our E is 499.2 divided by omega, which is 1040 RPM. Therefore, the new KE is equals to, let me see the answer that I've calculated. So it is 519.2 RPM. I'm sorry, this is not it. So I'm sorry, this make a mistake. This is not the answer for KE, but nonetheless, if you want to calculate KE, you have this over here, E divided by omega. So, but what we want to look at is basically what happened if the voltage equals to V equals to 250. So at 250 volts is different from 500 volts. So the E, our E would also be different. So let's find first the E if we have our voltage supplied to the machine equals to 250. So just as in previous calculation over here, E equals to V minus IR. Therefore V this time is equal to 150 minus I is 0.8 multiplied by R 1 ohm. So 250 minus 0.8, we got 249.2 volts. So the new E, when our voltage is equals to 250, is 249.2 volts. So getting our E over here, we can go back to the second equation where we have E equals to K E multiplied by omega. Therefore, the omega that we will have now with E equals to 249.2. Omega will be equals to E divided by KE, right? So our E now is 249.2 divided by KE. Our KE is over here, 499.2 divided by 1040. So 499.2 divided by 1040. So you will get at the end the answer of 519.2 RPM. Okay, so the rotational speed of the motor, as you have a voltage of 250 volts. So at 250 volts, your EMF, back EMF will become 249.2 and the speed will become 519.2. So in comparison to the speed that we have just now, right? So the speed that we had just now, it was 520, considering that if you consider that the frictional torque is negligible, but if you consider the frictional torque which can be observed through the current that is equal to 0.8, we will basically get the real RPM, that we will have later equals to, I mean not real RPM, of course, because the frictional torque will most probably change as well in function of the speed. The 0.8 will not always be 0.8. So, but let's consider that the torque will always generate, the frictional torque will always generate 0.8 amps. Therefore, we will have considering this torque, we will have an estimated rotational speed at 250 volt voltage equals to 519.2 rpm. So there is a bit difference of 0.8 rpm. So the speed is a bit slower, fractional, very small, slower, in a very small scale. The speed is lower, but nonetheless the speed is lower due to a certain frictional torque. Okay, so that's a bit on the first part of DC motor, introduction on the construction of the machine, the importance of different part like commutator and branch, and then we have seen mostly the first basically operating mode of DC machine, operating in steady state, and we have looked at steady state in the condition where we have no load. So in coming weeks, we are going to look at other characteristic in other part of operation as well, not just with no load. We will look at a steady state with load, and then after that we'll look at the transient state where we have difference of speed. For example, we will have acceleration in the operation. So that's all for this week lecture and a bit of tutorial. I'll see you next week. Thank you very much.